Hello, this is Mr. Craig, and this is Period 1's quiz. Actually, it's the first quiz. As I've said in the other videos, please don't just watch this video. Actually answer the questions so that you know what you got right, what you got wrong. Don't just watch the video in hoping that you'll learn something. The whole point for me to give these quizzes in class is not to ruin your grade, but it's to force you to, or not necessarily force you, but to help you understand what topics you may not fully understand and to help you review. So, again, these quizzes, not everybody has the same quiz, so these are different questions. And I think that the best way to learn something or to review something is to attempt it, make a few mistakes, learn from your mistakes, and then do better the next time. So let's go ahead and get right into this. Alright, so you've already taken the quiz. If you haven't taken this quiz yet on paper or at least written down your answers, I highly recommend that you stop this video or at least pause it, take the quiz under the 24-minute condition here. Okay, so you have 24 minutes to take 20 questions. That's the standard time, 1.2 minutes for each question that you'll get on the AP exam. I highly recommend that you do that. Don't just watch the video hoping that you'll learn something. All right, questions 1 through 3 refer to the following items. Select one letter choice that best fits each statement. A choice may be used once, more than once, or not at all. And again, especially on these first type of bang-bang questions, you're going to have, like in this case here, you'll have 5 possible answers, and then you'll get a series of questions that refer to those 5 questions. These should be machine gun style or type. In other words, you're going to answer these quickly. It's either you know it or you don't. There's no calculations that should be performed. But again, the key here is you can use an answer or a choice more than once. All right, so number 1, produces hydrogen ions in solution. Well, let's go through what each of these things are. Bronsted-Lowry acid. When we talk about a Bronsted-Lowry acid, we're talking about a substance that actually donates hydrogen ions or protons. So we're looking at an acid. Arrhenius acids do something along the lines of where they produce hydrogen. And I just answered your question there. For example, an Arrhenius acid doesn't have to be a strong acid, but typically they are. Will dissociate and we form hydrogen ions. So that's what an Arrhenius acid is. A Lewis acid is a little bit different than a Bronsted-Lowry acid, and actually it behaves oppositely. So when we talk about Bronsted-Lowry acids, they are proton donors. When we talk about Lewis acids, they're electron acceptors. Okay, so the difference is, as an acid, they donate. As a base, they accept. So when we talk about identifying something as a Bronsted-Lowry acid or a Bronsted-Lowry base, the rules don't change for Lewis acids and Lewis bases. It's still an acid. However, it's what's happening that's different. So if we have a pair of electrons, like in ammonia, NH3 has a pair of electrons that are not hooked up with anybody, and it has space for one more hydrogen to be placed on that. So it has that pair of electrons that's saying, here, I'm willing to share, donating, not giving them away, but allowing the Lewis acid to accept it. So in that case, water would be acting like a Lewis acid. Here, let me draw this out for you. The equation, I don't know if I have any space here. So if I have a Lewis acid, we'll put my hydrogens, can't do it there. My hydrogen here, 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 and I've got a pair there, and a hydrogen ion that has no electrons. This is considered the acid because it's accepting, again, accepting that pair of electrons from the base. So, and the Lewis base has this pair of electrons that's saying, hey, I'm willing to share it, come on over. So the acid comes over and it's an electron pair acceptor where the base is the donor. So I kind of knocked out the definition of a Lewis base as well. So it's an electron pair donor. And again, I'm using that term loosely because when we think about accepting and donating, it's a giveaway. But it really is not. Bronsted-Lowry bases are proton acceptors. Okay, so again, the difference on Lewis and Bronsted-Lowry, when we talk about terms of accepting and donating, they're opposite. All right, so I think we answered quite a few questions there. So produces hydrogen ions, we said that was B, areneous acids. Looking at the next one, accepts protons. Well, another way to say protons, it's a hydrogen ion with no electrons. So a proton is a hydrogen ion, so it accepts protons. So if it's accepting protons, then it has to be a Bronsted-Lowry base. So 2 should be D. An electron pair acceptor, we just talked about that as well. So we're talking about Lewis acids that are accepting that shared pair. So C. All right, so again, make sure that when you see these types of questions, you can't go into that much detail, but at least when you're reading through the questions, and again, I'm going over an over-detailed explanation for these things so that you guys hopefully can understand where these questions are coming from and why they're asking them. All right. Let's see here. I'll try to scrunch it so we don't actually show the answer. Number 4 asks, what is the missing product in the following nuclear reaction? Again, we love nuclear reactions, and you'll see these, hopefully at least 1 or 2, if not 3, on the multiple choice portion. But the beautiful thing is, treat that arrow like an equal sign. So we want to make sure that the numbers on the bottom all add up. We want to make sure that the numbers on the top all add up. However, if I'm giving you a coefficient, now you have that as a multiplier. So there's 4 on top, 0 on the bottom. So when we add these up, our total here, we have 140 already given. Well, we need 236, so whatever 236 minus that. And then we have 53 on the bottom and 92. So that means that we're going to have 39 on the bottom. And then whatever 236 minus 140 is, not doing real great on this, so 96, I think. And again, this identifies what we're looking at, so hopefully that's C, if I did my math right. Good. So again, most of the time you'll see that the coefficient is a 1, or there isn't a coefficient. But if you see one on the exam, I've seen it here lately, so be wary of that. Trust me, nuclear equations are probably the easiest ones to recognize. All right. Number 5. Okay. For the reaction where we have sulfate ions plus 10 hydrogen ions plus 8 electrons, this is a redox equation, and then it makes the S2O3 negative 2 and 5 waters. Choose the correct statement from the following list. The sulfur is oxidized. Well, if it's oxidized, that means that it loses electrons, and it looks like we're gaining electrons, so we know A's out. The reaction occurs at the anode. Well, these two actually represent the same thing. When we talk about reactions that occur at the anode, it's anox. In other words, at the anode, oxidation takes place, and red cat. So reduction takes place at the cathode. Okay, so that's one is out as well. Oxidation state of sulfur does not change. Not sure about that one. And D, the reaction occurs at the cathode. I would surely hope that it does. So I'm guessing D is correct because I know I can eliminate E. So if it's saying which one's true, well, we know that this is taking place at the cathode. So we don't even need to see if the charges change on that. And again, that's a time-consuming question. So D should be our correct answer, or best answer. And again, remember, multiple choice, it's a sprint. It's not a nice, long, leisurely run or long bike ride. So don't overthink the problem. Find out which ones you can eliminate right off the bat. If you find the correct answer, reread the question real quick and ask, okay, from this the statement, choose the correct statement from the list, and do be concerned about these little tricks down here. Oh, both A and B, or both A and D, and all that. So be careful. All right, number 6. Okay. All right, so let me scoot that down just a hair more. All right, so we have our reaction given above. So we have N2O4 to gas, 2NO2, which is also a gas. Goes from 1 to 2 particles. There's one thing. Our delta H has a negative value, so that means that we have an exothermic reaction. Kind of nice to know. Also, since this is exothermic, we can treat energy as a product, or on the right-hand side. Good things to look at real quickly here. Says, here's the question. An equilibrium mixture of the compounds listed above is placed in a sealed container at 150 degrees. The amount of product may be increased by which of the following changes? So we're looking for a way to increase the NO2. Adding 1 mole of argon to the container. Well, I don't see argon anywhere in this equation. Plus, I know it's a noble gas, so I'm going to consider that an inert gas. An inert gas. An inert gas means that it's unreactive and doesn't change anything. Also, you may wonder, well, it's increasing the pressure of the container. Okay, but it's increasing the pressure on both sides, the reactant product side. So we know one is out. Increasing the volume of the container. Well, if we're a system at equilibrium, and we have the double arrow there, if I go from a small container to a large container, what does this favor? Well, it'll favor the formation of the thing that has more particles. So again, we have one particle. Actually, I can't erase that. Let me erase these guys. Okay, so we go from 1 particle to 2 particles. And if we increase our container, as long as the temperature doesn't change, and it's assuming that it does not change, I don't see it changing anywhere, then it will favor the shift to the right. So 2 is looking very good. Raising the temperature of the container, well, that's why we go back to our exothermic. If we raise the temperature of the container here, okay, what does Le Chatelier say? Well, since this system is at equilibrium, and it's an exothermic reaction, anytime that we add anything to a system at equilibrium, we shift away from the addition. So energy is going to be treated just like a reactant or a product. So since we're adding more energy, it's going to shift away from the addition, and energy is a product since it's exothermic. So that means that we're going to decrease the amount of product to form more of that. So my correct answer should be 2 only, which looks like C. Okay. Which of the following, hopefully I didn't reveal the answer there. Which of the following substances is least soluble in water? Got to know solubility rules. You just have to know solubility rules. Okay. We have ammonium, soluble. We have potassium, soluble. Let's skip C. We have nitrate, soluble. We have sodium, soluble. Just by doing that, finding out what things I have that are soluble. Group 1A, all those are going to be soluble. Ammonium, going to be soluble. So when we talk about carbonate, okay, it will form a precipitate. So when we say least soluble, yeah, we talked about weak salts. So again, the thing here is we have the thing that has a low K value here, or KSP. Okay, so, and one of the sayings that I have here with carbonate, cold beer, Pizza Hut, so not soluble with carbonate. Okay. All right, number 8. Oh, shoot. Choose the conjugate base from the following reaction. Make sure that you can determine acids and bases. And here's how we do this. So we want to find the acid. We want to look at the before and after, so split it in half. Here I've got 4 hydrogen. Here I only have 1 hydrogen. Here I have 3 hydrogen. I'm only looking at the end because these guys aren't changing here. And here I have 2 hydrogen. So what this means is that this thing gave a hydrogen to the hydroxide. To get it back, that gave a hydrogen away. And again, we're only caring about the conjugate base, so we're looking, choose a conjugate base for the acid. So here's my acid. So my conjugate base, conjugates are always on the product side. There's my answer there. So whatever, looks like C. Okay. All right. Number 9. Where's the thing at there? Okay. The reaction given here, where we have nickel carbonate plus chromium, and it's a single replacement reaction. Which of these is the oxidizing agent? Well, I like this. Now, you won't ever see a choice like this on here, but obviously we wouldn't choose E. However, if you see a question where it's asking for an agent, you only have 2 choices. or you only have choices that are on the reactant side. So you may have some things that don't change, and so you may have like 3 or 4 reactants, and that's okay. So we have to identify in that situation which things are being oxidized and which things are being reacted. So if we're looking for the oxidizing agent, we're looking for the thing that contains the ion that is being reduced. Okay, again, remember the agents allow for the other thing to do what it's saying here. So the oxidizing agent is the thing that's reduced but allows the other item to be oxidized. So it can be reduced or gain some electrons. Alright, so nickel goes from a +2 charge, chromium's no charge. Over here, nickel's no charge, chromium is a +3 charge. So it looks like nickel has gone from a +2 to a 0. It's become more negative. And what that means is it's being reduced. So if I look at nickel +2, gaining 2 electrons, becoming just regular old nickel, that is reduced. So the agent is the thing that contains the nickel +2. So A is your answer. Okay. Don't ever pick something like that. Okay. You might say, oh yeah, it's nickel. No, it's technically nickel +2. So we have to find the thing. And the agent is the whole package. So when we talk about the agent, we have to include everything that thing that's being oxidized stays within. Okay, let's see here. Oh, crow. What happened? Sorry about that. So I think we're on number 10. Okay. Alright. I don't know what I hit, but I'm sorry about that. Alright. Here we have a reaction mechanism. And it says the above represents a proposed mechanism for the reaction of NO2 and CO. What are the overall products for this reaction? So again, if we're looking for the overall, then we want to cancel out alike terms. So we'll cancel out all intermediates, and actually we'll cancel out any of the catalysts if there are any. Well, O2 looks like it's an intermediate. An intermediate by definition is something that is produced and later used as a reactant. So the O2 is gone. Looks like nitrogen is also an intermediate. It's something that's produced and later used as a reactant. I noticed here, I'm glad I didn't go too dark, but I have 2 oxygens. So I'm going to actually cancel another oxygen out, and I'm going to put that one back. And it's okay. We're going to cancel both of those oxygens out. So we have 1 left. Is there anybody else that can get canceled? NO, CO. Looks like we're good here. So mechanism for what are the overall products? So it looks like we're going to have 2 CO2 and 2 NO. So what would the best answer? E? Looks like E is going to be our winner. Okay. Yeah, even though we don't have the coefficients on there. Okay. And there's the overall reaction. Again, I would not spend the time writing that out. That's simply there for you guys. Alright, I like this question because I've seen it quite a bit here. Alright, number 11. In the reaction where we have hydrogen plus nitrogen yields ammonia. The Haber process. Is at equilibrium. Okay, so it's at equilibrium. Check. Now, what we want to recognize is that the temperature goes from 300 to 250. Now, when the temperature was at 300, we had 65% of this reaction was products. Okay. Now, when the temperature changed, because when the temperature changes, your K value will change. When your K value changes, that means that your concentrations will also change. Your concentrations will never be the same when the temperature changes. Your equilibrium constant will change when the temperature changes. No ifs, ands, or buts. There's no exceptions to that. They change when the temperature changes. Alright, so here's the first thing that we want to do when we look at a question like this. We first of all want to determine the shift. So as we go from a temperature of 300 to 250, what has happened? Has the reactants made more products, or have the products made more reactants? Well, if it goes from 65 to 58, that means that some of the ammonia has decreased, which means that the ammonia has been converted back into hydrogen and nitrogen. So there's a shift toward the left. Okay, now we have to find out why that reaction shifted toward the left. Well, it's all dependent on temperature. When the temperature went from 300 to 250, we decreased or we removed energy from the system. Just like Le Chatelier says, that when you remove something from a system at equilibrium, it will shift toward the removal. The arrowhead is pointing toward the left. So what we want to do is we want to put energy toward the left. So what that means is we have an endothermic reaction. So here we go. Now that we know where the shift is and what side the energy's on, we can now come over here and answer the question. Does not shift to the right, so you can cancel out A and B. You can always determine this from the data given. So now we're down to C and D. And since energy is on the reactant side, that is endothermic, so D. You will see a question like this on the AP exam. If not, I'll be very, very upset, because this is a good concept question. Okay. If you need to pause and read that, that's fine. And I highly recommend that you go back and read the Le Chatelier information that I gave you guys all in class. So don't ever shy away from Le Chatelier. That's a huge concept in chemistry. All right. Number 12. Critical point. Okay. The critical point on a phase diagram. Now, again, when we talk about a phase diagram, and again, I'm kind of drawing this rough here, so I apologize. I know it doesn't look that good. We have pressure versus temperature, and in the phase diagram, we have a triple point, and this is talking about a critical point here, which would be somewhere around there. And again, my drawing's not to scale. It's not perfect, so I apologize. But here's our phases. We have solid, liquid, and gas. So there's your phase diagram. And the question's asking about the critical point of a phase diagram. Now, let's talk about the triple point, because that's probably the most interesting point here. But a triple point is a temperature-pressure relationship that allows us to see this substance as a solid, liquid, and gas in all three phases at that certain pressure and temperature. Everything has a triple point. Okay. Also, if we look at a pressure and a temperature and it happens to lie right on one of those lines, then it can exist in both of those phases. So it's going through maybe a heat of fusion, heat of vaporization, heat of condensation, whatever. So it's going through a phase change. So that's okay. We can have that. So the critical point right here states that when we look at a gas, no matter how much we compress this gas, it has so much energy that we can no longer change that gas back into a liquid. Now, do realize that we can take gases and compress them. And if we compress them enough, they'll turn into a liquid, which is kind of nice for industrial purposes. I mean, we do it with liquid air. We do it with propane tanks. We do it with all types of industrial processes where we need to use a gas for some reason, but it's not economical just to fill a can with the gas itself and not compress it enough into an aerosol, so to speak. So the critical point, the temperature is so high and those particles have so much energy that there's no way that we can get that to turn back into a liquid. So whichever one, oh, looks like I just said it here. So D. Okay. All right. Let's scroll that down. All right. Which of the following will occur spontaneously at high temperatures? Well, and then, even my own students are upset by this because you don't get the equation sheet. I honestly don't know why they don't give you the equation sheet, because I think that's dirty. I really do. And I wouldn't expect AP students to have to memorize something like this. I mean, we don't use this equation often enough for you to have it memorized. But, daggone it. Try to remember this equation and know the situations here. So, the question's asking for you to determine this spontaneously at high temperatures. We want to know what it is when it's spontaneous at all temperatures, low temperatures, high temperatures, and when it can never be spontaneous. So let's run through all those scenarios while we've got a question like this. First and foremost, for it to be spontaneous, delta G has to be negative. Okay, so we can automatically eliminate E and C right off the bat. Okay, and again, I'm going for all temperatures right now. What we also want, and no matter what the temperature is, if the hydrogen is negative, that's a very favorable situation. Temperature, well, temperature is always going to be a positive value because we always have it in the unit of kelvins. So Kelvin scale starts at 0 and goes up. There are no negatives. However, delta S deals with entropy, randomness, chaos. I know a lot of people argue that term chaos, but I like it because it helps to describe how unorganized the universe wants to become. So if the universe wants to increase its entropy, we should have a positive value for that delta S. So these are the conditions at any temperature that this will be spontaneous. All right, so the next scenario, let's answer this one at high temperatures. So if the temperature is high, what that means is we've got a really, really high temperature here. So that's going to help us win out. We can have a positive value here, or an endothermic value, and our entropy will also be positive. So when we look at high temperatures, think of it like this. Positive is above 0. It's high. Okay? So you'll have a positive delta H and a positive delta S because our temperature is really, really high. So even though our delta H is high, we really want to make this back end of the equation negative by making sure our delta S is positive. So this is at high temperature. So I think I just answered the question there. So looks like D is our answer. Okay, well, let's go on. Let's talk about low temperatures. Okay, well, we know that we have an exothermic reaction at low temperatures. However, in some cases, our delta S may have a negative sign as well. If the sign is negative, then we want to make sure that our temperature is not going to overthrow the value of delta G. So we want to make sure that T is kept low because our delta S is causing this back into the equation to turn into a positive sign. So we want to make sure that our delta H is high enough to keep the delta G as a negative value. So at low temperatures, below 0, low. And then there's a scenario, regardless, or doesn't matter what the temperature is, if I have an endothermic reaction and the system's becoming more ordered, it doesn't matter what the temperature is. That thing will never, ever be spontaneous, mathematically speaking. So make sure that you know all 4 of those scenarios. That's a huge concept. It's not only asked in the multiple choice, but it's also asked in the free response portions of the questions where you don't get to use a calculator, but sometimes you have the equation sheet in the free response. All right. Number 14, which of the following is false? Okay. 4d orbitals are in the fourth period on the periodic table. Hang on here, let me whip up a periodic table if I have one here. Thought I had one here. Okay, here's one. Come on, open up. Shoot, I don't think I'm going to be able to open that. Sorry guys, can't see it. Grab your periodic table and take a look at this. 4d orbitals are not in the 4th period, or the 4th row on your periodic table. Remember that the S and P orbitals are in the same period or same row as the energy level. However, the d orbitals are one less than the row they're in, so the 4d orbitals are actually in the 5th row. If we talk about f orbitals, they're 2 less than the rows that they're, or the period that they're in. So that's what makes this a true statement, where this is false. So right off the bat, we got A. Okay, and then the other ones, hopefully you know that s orbitals are spherical in shape, p orbitals are dumbbell shaped. And the nice thing is you don't have to know the shapes of the other. Just know that they get more complex as we go from P to D to F. And no, you'll never be asked to draw those, the P, the D, and the F's. All right, number 15. In the following diagram, which label which label arrow represents the heat of reaction, the delta H, for the forward reaction. Okay, so forward means that we're going to start right here, and we're going to go to right here. So the reactants have a certain amount of energy. The products have a certain amount of energy. Bingo, we just answered it. Okay, so remember, based on our equation, that when we talk about heat of formation, it's the sum of the heat of the products minus the sum of the heat of the reactants. And that's on your equation sheet, but guess what? You don't get that equation either. So when we talk about each of these letters, and let's take a look at this, let's talk about what each letter actually represents. So A is our answer. Okay, we'll go right off the bat there. So that's our delta H value. B, what does B represent? You might say, well, that's nothing. But really, the reaction, if it's reversible, that's how much energy we start with, and that's the amount of the activation energy for the reverse reaction. So B does have something that is significant. C is the activation energy for the forward reaction. In other words, activation energy allows for our reactant to change from a reactant to the activated complex, which is at the top here. And what is the activated complex? It's that transition where it's no longer a reactant, not really a product yet. But once it goes over the hump, now we've got a product here. So that's the activated complex. The amount of energy to form the activated complex from the reactants or reactant. D's kind of a nonsense thing, but again, it does play a somewhat important role. It tells us what our amount of energy is for the reactants. And we don't have a value for our products here, so if we had another arrow, that would be the amount of energy for our products. So A should have been the correct answer for 15. All right. Here we got a rate law. Love rate laws, and you should too. And let's describe what a rate law is. And again, this is from our kinetics equation, or our kinetics section. Rate, again, is molarity per unit of time. Okay. K, a constant. So the constant will have different units based on what the orders of the reactants are. So that's a constant, K. M, what order is M? Well, M is a first order reactant. How do I know that? Because there's no number there. So that implies that that's a 1. If that were a 0, then M would be a 0 order reactant or not shown. N definitely is a second order reactant. So let's talk about the characteristics of first and second orders and 0 order, even though 0 is not on there. When we talk about a 0 order reactant, doesn't matter what the concentration is. The rate of the reaction remains the same, regardless of how much we have. So if we have a 0 order reactant, no matter what the concentration is, that rate remains the same. If I have a first order reactant, if I double the concentration, then I double the rate. If I go triple the concentration, then I go 3 times faster. So it's directly proportional there. However, if I look at a second order reactant, if I double the concentration, I go 4 times faster. If I triple the concentration, I go 9 times faster. If I quadruple the concentration, I go 16 times faster. So it's exponential growth. All right, so having known that, let's answer the question. The rate of a certain chemical reaction between substances M and N obey the rate law above. The reaction is first studied with M and N each at 1.01 molar. If the new experiment is conducted with M and N each with a, now it's going from that to that, so our concentration has changed from 0.001 to 0.002, so we've doubled the concentration of each. The reaction will increase by a factor of what? Well, okay, so we've doubled the concentration of all these. Let's go ahead and, so if I double the concentration for M, it's going twice as fast. If I double the concentration for N, it's going 4 times as fast. So if that goes twice as fast, that goes 4 times as fast, then we're going to go 8 times faster. E. Pretty simple. Now, here's a question that wasn't asked, but could be. What's the overall order of the reaction? If you're looking for the overall order of the reaction, add 1 plus 2. So the overall order of the reaction is third, or 3. Now, that could be any value. Order of reactants, 0, 1, or 2. 17. Oh, you got to love this. Mixtures that would be considered buffers include which of the following? All right, the first thing that we have to realize when we're looking at a buffer, and I'll admit we didn't spend too much time on buffers, and I really regret that, and I wish that we could do more with buffers because it is a pretty important type of system. But the key here is that when we're looking at a buffer, we are looking at a weak, either acid or base, doesn't matter which, and it's salt. Okay. In other words, we're looking for something that contains a common ion of that. So if I'm looking at, say, here's a weak acid, HNO2, not HNO3, nitric is very strong. I want to find a salt that has that common ion. Now remember, the H right here is what makes this an acid. So it's a weak acid because it's not strong. And what does strong mean? It dissociates 100%. So when we look at the salt here, the sodium's not going to do anything. However, the nitrate is my common ion. So when I look at my buffer solution, I have nitrite ions on the right-hand side, and then I have some HNO2 on the left-hand side. And the nice thing about buffers is they can handle any strong acid or strong base if you add it to a buffer that has significant concentrations. So one thing that we never ever can have in a buffer is a strong acid or a strong base. So having said that, gone. So really only two. Okay? Know your strong acids. Know your strong bases. If you know your strong acids and your strong bases, questions like this become very, very easy, and you can answer them very, very quickly. Okay. All right, number 18. In which of the following species does sulfur have the same oxidation number as it does in H2SO4? Well, real quickly, SO4, okay, we know that oxygen is going to be a -2, so total -8, so sulfur has a +6 charge here. No way it can be the same in sulfite. Charge of SO4 and SO3 are the same, so there's no way it can be the same charge. Let's skip that for we can do that. All right, so oxygen, we have 3 oxygens here, so total charge of -6. And then we have a -2, so really, that doesn't give us much of a choice. So +1, that's odd. Okay, so yeah, that would, boy, that's really ugly. Boy, that's the easiest one there. -2, no. Sulfur, all by itself, no charge. I don't even have to do the calculation. Okay, so do real quick math, especially if they were giving you the charge. Remember, anything by itself should not be excited. Okay, so S8, no charge. Okay, and I honestly, I didn't need to find the charge for E. All right, 19. Which element has electron configuration that does not follow the all-ball principle? In other words, when we go and write out like 1s2, 2s2, 2p6, 3s2. In other words, we're dropping electrons in those orbitals as we go through them, okay, in the order that we actually see it. Do realize that there are, within the transition metals, there are some special stability rules. So we have to look at the periodic table and ask ourselves, can we have these certain situations? I'll go ahead and pick it out. Nickel. Nickel's one of those situations where we could have either a half-filled S or a half-filled D orbital. Okay, half-filled means S has 2 electrons. We can take one S out and put it in the D, and I think that's our scenario here with nickel, where we, and I can't pull up the periodic table, but I'm pretty sure that's the scenario. Or we can take 2 out. Again, look on your periodic table where nickel's at, but it can have one of these 4 scenarios. So half-filled S, half-filled D, empty S, in other words, removing both electrons from the S orbital, and it's got to be in that same energy level. I'm sorry, same period. So when we look at the, say, the 4s orbitals, we can only work with 3d orbitals to drop electrons in. Why can we do that? Because this is a higher energy level, and they want to go to the lower energy level, if possible. However, they're just not going to go voluntarily. They'll only do it for certain situations. So make sure that you know half-filled S, full D, empty S, full D. Those situations do exist. Why does that happen? That's just the way nature likes it. And last but not least, all right, what is the voltage? What is the voltage if the following half reactions are combined in a galvanic cell? Again, galvanic cell, we're always looking for a spontaneous reaction, which means we must have the most positive voltage. So in this case, if we leave this alone, we're not going to have the most positive voltage. So we need to flip this equation, and we're going to have potassium metal being oxidized to form that and that. So when we do that, we have a positive 292, and then add it to that negative 0.13, and what does that give us? This? I think so. That's the closest one, B. Okay. Now again, I'm going to try very hard, and I don't know how long this actually took right off the bat here. I want to make a video for each one of these quizzes to help you guys review. So, but please, 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 at least attempt the quiz before you watch the video. And I know there's a lot of great information that's being said as I'm actually answering these questions. And I know I go outside of the box and I start talking about other things that the question may not be related to. But at least try the questions first. You might accidentally learn something as well. As always, I hope this video has helped. And if you have any questions, don't hesitate. Please email me.